Welcome to my video on Extrema on an interval. What we're going to be looking at here when we talk about Extrema, we're talking about when a function achieves a maximum or minimum value on the interval. And we're going to be looking at this in terms of a closed interval and an open interval. So our objectives for this particular video are: 1, understand the definition of Extrema of a function on an interval. Number 2, understand the definition of of relative extrema on a function on a open interval. And third is to find extrema on a closed interval. Let's look at a definition of extrema, what it means to be an extrema. We're going to let f be a function that's defined on an interval containing the number c, x equals c. And what we have on this, f of c is a minimum of f on that interval I when f of c is less than or equal to all f of x for all values of x in that interval I. So in other words, f of c is a minimum if it is the smallest value that the function achieves on the interval. Then we go to maximum. F of c is a maximum of f on the interval I when f of c is greater than or equal to f of x for all x in I. So looking at the two diagrams I have here, in this case, we have a minimum at this particular value, at that c, because it is the smallest. It's when the function actually achieves its lowest value. And in this case, this would be a maximum of that function, which would be at x equals c. So f of c here is a maximum, and on this one, it is a minimum. And that's what it means to be an extrema of a function. Now, the next thing we have is what's called the extreme value theorem. Now, it's very important here on this one in terms of the conditions, that f is continuous, it must be continuous, and we must be looking at this on a closed interval. So, if f of x is continuous on the closed interval from a to b, then f has both a minimum and a maximum on that interval. Now it's important again that you have both of those conditions. Let's look at this graph over here, this first graph. So we'll call it, in this case, this will be graph 1. Graph 1 is continuous on the interval from a to b, so we'll say there's a, and we'll say here's b. It's continuous on that interval, and it is on a closed interval. So that means it's defined here. So in this case, in this particular instance, we know that this, by the extreme value theorem, I will have a maximum value and a minimum value on that interval. So in this case, we achieve our minimum value right around here, and our maximum is at the endpoint that we have right up there at b. In our second graph, so we'll call it graph 2. Graph 2, what we have here in this case, we're not including the idea that we're on a closed interval. We are actually on an open interval in this case from a to b. So a is going to be here and b will be here. And in this case, what we have is that we do have a minimum value. It occurs right here. We have that minimum, but we don't have a maximum. At this location right there, that's an open interval. So we just keep getting closer and closer, but we never actually reach it. So if I sit there and say that, oh, I have a maximum at a number, there's always another number further on. There's always going to be, between any two real numbers, there is another real number. So I can't sit there and specify a particular maximum value on that because there's always going to be one further on, because I'm at this point it's an open circle, so I keep getting closer and closer, but I actually never reach it. Also, it's important to remember as well that this condition would still be true if it was closed, if we included the point at A but not at B. Okay, that one would still have, we would not have a maximum on this one. Our third graph, so graph 3 in this case. In that case, what we have is we're violating the continuity. And in this case, we do have a maximum. Our maximum is going to be at the endpoint as it was in graph 1, but our problem is right here with the minimum. We do not, because it's not continuous, we keep getting closer. As we come in each direction, we keep getting closer and closer to that point, but we never actually reach it. And so again, the same issue we had in graph 2 with the maximum, we now have in graph 3 with the minimum. Now that we've looked at what it means to be an extrema and the idea of the extreme value theorem, now we're going to go and kind of take it back a little bit. We're going to deal with what's called a relative extrema. Looking at the other versions where it was the highest value or the lowest value, those are what's called an absolute or global maximum or minimum. Those are a little bit harder to deal with. So what we work with here is we're going to work with what's called a relative extrema. And really what this means is that if we have an open interval that containing C on which f of C is a maximum, or you'll notice I put in pink minimum so you can interchange maximum and minimum, where f of C is a maximum, then f of C is called a relative maximum. Now it's in this open interval that we have this. So it's an open interval which contains C. Then it's called a relative maximum of f, or you can say that f of f has a relative maximum at C f of C. And again, you can go ahead and replace maximum with minimum, and you get the definition of a relative minimum. Okay. Now, it's important to keep these things in mind because these relative minimums and relative maximums do not have to be the highest value that the function achieves or the lowest value the function achieves. While those certainly would be considered relative max and mins in some cases, there are going to be values that are relative minimums that are actually not the overall lowest value or overall highest value. Here's a couple of examples that we can use to kind of illustrate that fact. In the first graph that I have right over here, we have a function that's defined over all real numbers. And what we have here is all the low points. So here and here at A and C, we have relative minimums because I can take just a small portion on the side of A, around A. I can go through just a small part, so here and here. And my function achieves its lowest value inside of that interval at A. The same thing would be true at C. If I went through an open interval just to the side of C, I would have my lowest value is achieved at C, and all other values inside of that interval would have all the x values would give us a higher function value than what we get at x equals C. In this case, we also have a relative maximum. That relative maximum is right here at B. It would be f of B. So, and again, for the same idea that I could create an interval, an open interval around that includes B, where f of B is the highest value that we achieve in that interval. Okay. Notice over here as well, in the second one, in that first graph, both sides went up, and we did have, in this case, we did have a global or absolute minimum at C. That does happen to be an absolute minimum, but it also would be classified as a relative minimum as well. In our second function, again, the domain is all real numbers on this one. It is a polynomial. And you'll notice that we do have relative minimums, again, in this case at E and G. That's where the function does achieve where I can create open intervals around those values, at E and G, where f of E and f of G would be the smallest values. And it does have relative maximums at D and F. So notice on this one here that while we do have two relative minimums and two relative maximums, we do not have any global minimum or global maximum because of the fact that our function continues on in both directions, one going up and off to the left going down. So in this case, we didn't have a global max or min, but we do have two relative max and two relative mins. Where in the first case, we did have a global minimum, but we didn't have a global max because of the fact that the function did continue up in both directions. Now, much of what we're going to do in this section is really go through and identify where a function has its relative max and mins and where those happen to occur. So to do that, we need to have some tools that we're going to go through and get right now. The big tool that we have in this case is what's called critical numbers. The critical numbers tell us our values in our domain, where the derivative at that value is either 0 or undefined. So we're going to let f be defined at x equals c. If f prime of c equals 0 or is undefined, then c is said to be a critical number of f. Okay, those are going to be important things. And one of the things you're going to have to do is you're going to have to locate all the critical numbers. And it is going to come where that first derivative is 0 or undefined. So when you hear critical numbers, right away you need to be thinking, I need to find the first derivative and then identify where that's 0 or where it's undefined. So right now you are probably asking, why are critical numbers so important? Well, here's why. Because every place, wherever a function has a relative max or min, that will occur, those relative max and mins are only going to occur at critical numbers. So, relative max and mins, relative max and mins only occur at critical numbers. So that's why the critical numbers are so important, because if I'm going to locate where we have a relative max or min, that's where they're going to happen. Now, the other thing that's important to remember here is just because we have a critical number doesn't mean it's a relative max or min. If there's going to be any relative max or mins, they will occur at critical numbers. But just because a number happens to be a critical number does not mean that it must be a max or min at that point. Now let's take a look at a couple examples in terms of finding critical numbers. So let's take a look at our first example. Our first example is right here. It's f of x is x cubed minus 12x. I want to identify my critical numbers. So what I'm going to do in this case is I will take the derivative. And when I take the derivative here on that function, I will get that f prime of x is equal to 3x squared minus 12. Now, in this case, that's a polynomial, so it's never undefined. So my critical numbers are not going to occur when it's undefined. So the only place where I'm going to have critical numbers are going to be when this is equal to 0. So I'm just going to set that equal to 0. And I'll solve for x. So I'd get 3x squared, in this case, equals 12. Now, if it happened to be a trinomial or it was minus 12x, what we would have to do at that point would be to factor it. But in this case, I can just solve it. I divide by 3, I'll get x squared equals 4. So x is going to be plus or minus 2. So in this case, this particular function, f of x equals x cubed minus 12x, has two critical numbers, and those critical numbers are at positive 2 and negative 2. In the next example, in this case, f of x is the cube root of x plus 1. So the first thing I'm going to do, though, with that is I'm going to write that using exponential notation. So f of x, instead of cube root, it's going to be x plus 1 to the 1/3 power. And so I take the derivative of that, and using the power rule, I get f prime of x equals 1/3 times x plus 1 to the negative 2/3 power, which I can look at that and say that is equal to 1/3 times x plus 1 to the 2/3 power. Now in this case, I know that this would be, my critical numbers occur when our derivative, our first derivative, is 0 or undefined. In this case, particular problem, I know I'm not having any critical numbers when it's 0 because the numerator is already 1 and there's no variable up there. The only time a fraction can ever equal 0 is when the numerator is equal to 0. And since 1 can never equal 0, I'm not going to get any critical numbers by setting this equal to 0. Where we're going to get critical numbers are at the place where this fraction is going to be undefined. And the only place that fraction is undefined is when the denominator is equal to 0. And in this case, the only way that we're going to get a denominator equal to 0 is if x equals -1, because that would then be 3 times 0 to the 2/3 power. So in this case, my critical number, the only critical number I have, is when x equals -1. So that would be my one critical number on that particular problem. Now, the one thing you want to do if you want, take your calculators out right now and graph these two functions. What you'll notice in the first problem is that we do have a relative maximum is going to occur at -2, and we will have a relative minimum that occurs at +2. So our relative maximum on this comes out to be negative plus 24, so it's going to be 16. And our relative minimum would come out to be -16. In the second one, at x equals -1, if you take a look at that one, if you graph it out, what you're going to notice is we actually don't have any relative extrema with this particular function. It is a cube root, so its domain is all real numbers, but it is always, if you look at it, it is always really increasing. What's occurring in this case at x equals -1 is that we actually have a vertical tangent there, and so that's why this one happens to be undefined there. It's not that we're reaching any particular max or minimum value. It's just it happens. It has a special point, but we'll be talking about that special point later on in another section. So with all this information now we're going to go through finding extrema on a closed interval. Now, we know by the extreme value theorem that there is a global max and a global minimum on every closed interval. So what we have to do is we have to find it. So we have some guidelines. And to do this, what we have to do to find the extrema on of a continuous function f on a closed interval from a to b, these are the steps we're going to use. The first thing we have to do is find the critical numbers of f in that open interval. So I'm going to take the derivative and I'm going to identify the critical numbers of f. I'll end up probably finding all of them, but I only want the ones that are in the open interval from a to b. I'm not concerned about ones that are not in that interval because they're not going to have any bearing on the problem at all. Number two, I'm going to evaluate f at each one of those critical numbers. Okay, and I'm going to actually plug them in and I'm going to get the function's value at those. And the other thing I have to do, because we have a closed interval, it's important to remember that our maximum or minimum might not occur at a critical number, our global maximum or minimum. It might actually occur at the endpoints. So the next thing I have to do is I'm going to evaluate f at each endpoint of the closed interval from a to b. So I'm going to evaluate f at a and at b. And when I do that, I'll have all these different values, and the smallest one is going to be my minimum, and whichever one of those values of the function, when I evaluate the function at the critical numbers and at the endpoints, whichever one of those values came up to be the largest, that is going to be my maximum. Let's take a look at this example here. We're going to have, we have a function g of x, which is equal to 2x cubed minus 6x, and we're looking at the closed interval from 0 to 3. So because of the fact that we are looking, at this case, on an interval from 0 to 3, a closed interval, we know a maximum and a minimum does occur. Okay, in this case, I go through and take the derivative. I find g prime of x just by application of the power rule is going to come out to be 6x squared minus 6. Pulling out that factor, I get 6 times x squared minus 1. And I can say that g prime of x, is equal to 0 when x equals 1 and negative 1. Now the one thing I have to keep in mind here, yes, negative 1 is a critical number, but it does not fall in our interval. So I'm actually not concerned about the negative 1. So what I'm going to do now, at this point now I've gone through, I've found the critical numbers, and the only critical number I'm concerned with is at 1. So the next thing I do is I find g of 1. And g of 1 is going to be 2 times 1 to the third minus 6 times 1, which is going to be 2 minus 6, which is negative 4. So there's g of 1. And that's the only critical number I have. If I had other critical numbers, I'd plug those in and evaluate g at those as well. The other thing I have to do now is I have to evaluate this at the endpoint. So the next one, I have an endpoint. One endpoint is at 0, so I have to find g of 0. And g of 0 is going to be 2 times 0 cubed minus 6 times 0. Well, all that's just going to be 0 minus 0, which equals 0. And the last one I have to do with the endpoint is I have to evaluate it at 3. So I'll take g of 3 is going to be 2 times 3 to the third minus 6 times 3. Well, that is going to come up to be 54 minus 18, which in this case comes out to be 36. So what I know in this case is that I have a minimum. My minimum is at negative 4. That's my minimum, because it's the smallest value that I came up with. And the maximum is at 36. So the minimum value of g is negative 4. The maximum value of g is 36. The minimum value occurs at x equals 1, and the maximum value occurs at x equals 3. Now you're going to have to keep that in mind too in terms of verbiage that we use here, because sometimes they're going to be asking where does something occur, where does it happen, and other times they're going to ask what is that. So if the question was where does the minimum occur, the answer would be at x equals 1. If the question is what is the minimum, the answer is negative 4. So this now concludes my video on the extrema on an interval. Please keep in mind the idea of the extreme value theorem, that the extreme value theorem, because it's working with a closed interval, guarantees that the function will have a maximum and minimum value on that closed interval. It can occur at a critical value, or it could occur at the endpoints. Okay, we now have a method for going through and identifying where the extrema, whether or not the extrema occur at critical values or endpoints. You also know how to find those critical values. So keep that in mind, and in class we'll spend some time working with some of these functions. We'll also talk about how the calculator comes into play and some of the other differences that can occur in terms of when we have a maximum, when we have a minimum. So have a good evening, and we'll see you in class.